All right, and with that, good morning, everybody. Welcome back to Calc 1. Plan for today, we're going to finish off Standard 11 and then jump into Standard 12, talking about transcendental antiderivatives. It's antiderivatives of all of your favorite Standard 9 functions, in other words. The next office hours are on Monday at 11 and at 1. We are going to have a quiz on Monday over Standard 11. And I've also posted a web work homework 17, which will be due on Wednesday. Don't forget you have web works also due tonight and on Monday. So, before we get into the calculus, I want to talk about something. A couple of you have come asking me questions about courses for next semester. And since the course schedule is, I believe, scheduled to come out later today, that is what my sources tell me, unless I'm being lied to. So I thought I'd talk a little, and something I like to do in all the classes I teach is talk a little bit about, hey, what courses are coming up that might be kind of good follow-ups to the course you're currently in. And for you all, there's one primary course that kind of serves as a nice follow-up to Calc 1. You guessed it. It's Calc 2. So I thought I'd just briefly talk a little bit about what's Calc 2 about, who should be primarily interested in taking the course. And main idea behind Calc 2 is it's kind of going to be picking up right where we leave off in Calc 1 at the end of this semester. Calc 2 is going to be focused on kind of a variety of topics, including how do you integrate scary-looking functions, so a variety of kind of integration techniques like partial fraction decomposition, integration by parts, which is product rule backwards, etc., etc. Using integration to do things like find surface areas and volumes of various shapes. Looking at infinite sequences and infinite series. Talking about what happens if you add together infinitely many positive numbers. Is it possible to still get some finite number if you're adding infinitely many terms together? And finally, looking at different coordinate systems like parametric and polar coordinates. So, who should be taking, so, Dr. Nursel, who should be signing up for Calc 2? If you want to go on in math, you need to take Calc 2. If you want to study physics, you need Calc 2. If you want to study chemistry, you need Calc 2. If you want to study biochem, you need Calc 2. If you want to study biology, you do not necessarily need Calc 2. But it does serve as sort of like an option for like, you have to choose like, I was looking at the course catalog, and for a bio major, you have to choose like 5 cognates from this list of courses, one of which is Calc 2. So you could take Calc 2 in accounts, but you're not strictly required to. But other than biology, basically any of the other science majors are going to require you to take Calc 2 at some point. No, you do not need to take Calc 2 for a core math requirement. Core just requires that you take at least one math course, which you are, currently taking. Calc 2 is offered every semester. I would encourage you, though, not to wait too long before taking Calc 2 if you think you are going to take it. Probably be easier if you take it right after you take Calc 1, just so it's the calculus, Calc 1 stuff is fresher in your mind. But if you don't take it this spring, it is offered every semester, and I recommend you take it in the next soon-ish, let's say. But yeah, once you take Calc, those of you who are interested in going on and doing, say, like a math major or minor, once you take Calc 2, then the major sort of opens up. You can either take linear algebra or multivariable calculus next. And once you take those, basically you can take any of the math courses our department offers, pretty much. The only other math course I'll write down as something you might be interested in is our Math 105, Math and Deductive Reasoning. Which is our kind of core math course. Typically, most students don't usually take Math 105 if they're also taking calculus. Math 105 is sort of the non-calculus option for fulfilling that core math requirement that our department offers. But I will say that Math 105 is a very different sort of course than the Math 220 Calc 2. Math 105, instead of being primarily computation-based like this class is much more focused on ideas of logic. How do you construct a mathematically logical argument, sound argument, and then puts it into practice and studying kind of Euclidean geometry, looking at Euclid's elements. Math is not really a great book subject, but if our department did have one great book, Hillsdalian course, it would be that one, looking at primarily Euclid's elements, especially in the second half of the semester. Which, by the way, Euclid's Elements, second most published book of all time, second to the Bible. Puts all those other great books you learn about out of the water. Super important. But Math 105 is something that doesn't really fulfill any specific. If you have Calc 1, Math 105 doesn't really fulfill any specific requirements for anyone. Like, none of you would be required to take it for any reason unless it's just to get 3 more credits, I guess. But the Calc 2 is going to be required for any of the science majors other than biology. And even biology, I would never recommend it. No, it's a fun course. But both of these are offered every semester, I will say. Any questions or comments about math courses coming up? Yes, Katie?
Who generally teaches Calc 2?
Everybody. So both of these are courses that kind of get circled around the department quite a lot. So who's teaching it one semester will likely be different than who's teaching it the next semester, other than the fact that Dr. Murphy loves to teach him some Math 105s. I will say, I forget who's teaching 105 this spring. I know the 220s, though, will be in an unusual twist. It's actually the same people who are teaching 120 right now, meaning Dr. Gabler and I are each going to be teaching a section of the Math 220 Calc 2. And I will say, yes, if you go on to take Calc 2 with me, we'll be using a very similar mastery-based grading system. Yes?
Is it a 4-hour credit like this one?
It is, yes. Math 105 is a 3-credit course. All of our, well, other than the 112, 113 sequence, all of our calculus courses, Calc 1, Calc 2, multivariable, are 4-credit courses. So, just letting you all know, the Calc 2s are, there's going to be 2 sections, one at the very beginning of the day, one at the very end of the day. I will be teaching a 7:45 section of Calc 2 this spring. Dr. Gabler, 7:45 to 8:50, same time this class is. Dr. Gabler will be teaching a, I think, 2 o'clock to 3:05 p.m. section of Calc 2. But the times will vary from semester to semester, depending on when you take it, but Calc 2 will always be a 4-credit course. Are there questions or comments? If you have any kind of individual or like personal questions about whether you think going on to take Calc 2 or Math 105 might be a good fit for you, I'd be happy to meet with you outside of class or answer any questions that you might have over email. Just let me know. So, one day, a cannibal is buying brains for dinner at the local store. So he goes to the butcher shop, where he is told that mathematician brain costs $1 a pound, engineer brain costs $2 a pound, politician brains cost $10 a pound. Cannibal's bewildered by this, asks the butcher, why does politician brain cost 10 times as much as mathematician brain? Is quality that much better? Butcher replies, goodness no, but it takes 10 times as many politicians to make that 1 pound of brain. And with that, let's do some calculus. So when we left off last time, we had talked about what it means to take an indefinite integral or to find antiderivatives of a function, where we said that an antiderivative of little f of x is going to be a function big F of x with big F prime of x equal to little f of x. So in other words, we said that an antiderivative is like taking a derivative but backwards. An antiderivative of your original function is something that you can differentiate in order to get to your original function. And we said that the indefinite integral which we denote by this little swirly symbol, f of x dx, is going to be the family of all antiderivatives of a function little f of x, which can be Dr. Gabler's family if he really wants it to be, I guess. So in general, what do we say that all the antiderivatives of a function are going to have in common? Specifically, if we call it a family of antiderivatives, what's the relationship between all of the antiderivatives of a single function? Nathan?
Everything with a constant.
Yeah, they're going to be the exact same except for they could have a different constant term at the end. So as a quick example, if you want to look at what do all the functions look like that have an antiderivative of x squared, or that have a derivative of x squared, excuse me, well, it's going to be all functions of the form 1/3 x cubed plus some constant. These are all the functions, in other words, that have a derivative of x squared. And we had a formula, which was the reverse power rule, that says that in general, if you're integrating a power function, you're going to get x to the power of n plus 1 all divided by n plus 1. What am I missing? Nora? Plus c. Don't forget your constant term at the end. So you get all the antiderivatives rather than just a single one of them. Alright, so towards the end of class yesterday, I'd given you all some integrals to look at. Namely, integral of x cubed plus 5x plus 4, integral of 2 over x cubed minus 3 radical x, integral of 2t squared plus 3t cubed plus 1 all over 4t squared, integral of x squared over 3 plus 3 over x squared, and then another couple, which we'll throw up on the board here in just a minute. So last time, you all had the opportunity to kind of take a look at these different integrals. So I thought we would go over them today before moving on to standard 12. So start with this one. How are we going to integrate x cubed plus 5x plus 4? In other words, what would all of the functions whose derivative is x cubed plus 5x plus 4 end up looking like? Anna?
1/4 x to the 4 plus 5 halves x squared plus 4x.
Let's see. If we were to differentiate this, we would get 4/4 x cubed, so x cubed, plus 10 halves x, so plus 5x, plus 4, plus 0. I think it checks out. Neato burrito. How about 2 over x cubed minus 3 square root of x? Eden, I know that's not raising a hand, but I'm going to call on you anyways because that's the closest I saw to it.
Okay.
So, what was your approach for looking at this one?
Well, I rewrote the x in the denominator as a negative exponent, so 2x to the negative 3, and then I rewrote minus 3 to the minus 3 times the square root of x as minus 3 times x to the 1/2. And then for the derivative, I have negative 1 over x squared minus 2x times the square root of x.
Negative 1 over x squared. Can you repeat what you said?
Yeah, minus 2x times the square root of x. Plus c.
Goodness gracious. How did you get from here to here?
That's a great question.
Thank you. I'm proud of it.
Okay, so I added 1 to the 1/2, I added 1 to the 1/2 x. Oh wait, I have to do the first part first. Okay. You add 1 to negative 3, so it's a negative 2, and then you divide the 2 coefficient by negative 2, which is just negative 1. So it'll give you negative 1 over x squared.
Okay, so integrating 2x to negative 3 will give you 2x to the negative 2 divided by negative 2 using the reverse power rule, which is the same as negative x to the negative 2 or negative 1 over x squared. I'm on board.
And then you add 1 to the exponent 1/2, which is 3 over 2. And then you divide negative 3 by 3 over 2, which is the same thing as multiplying by 2 over 3. So the 3's cancel out and just give you negative 2. And then x to the 3 over 2 is the same thing as x cubed in the square root. So you're just taking x squared out and leaving 1x inside.
Gotcha. So the minus 3x to the 1/2 becomes minus 3x to the 3/2 divided by 3/2, which will simplify to minus 2 x to the 3/2 or negative 2 x root x. And then we got your plus c. Everyone on board? No. Quiet today, very few nods. Nod or shake your head. Or bobblehead if you're not sure about it. Yeah, I like it. So just like sometimes if you're trying to differentiate, if you're dealing with something that's a power of x, but it's not immediately written in the form x to some power, it can definitely help to rewrite it as 2 over x cubed, for instance, as 2x to the negative 3, or square root of x you can always write as x to the 1/2. And just this how writing those out can help you when you're differentiating, can also help you when you're integrating as well. Writing it out as x to some constant number power in order to be able to use the reverse power rule on that. Alrighty, how about this one? Integral of 2t squared plus 3t cubed plus 1 all over 4t squared. James, what was your approach for this one?
So first I broke the fraction up into 2t squared over 4t squared plus 3t cubed over 4t squared plus 4t squared.
Ooh, okay, so you just broke it up into 3 separate fractions.
Yeah.
Okay.
And then the first one just simplifies to 1/2. Plus
Swoosh,
3,
swoosh, swoosh.
and then plus 3/4 t. Plus 1/4 t to the -2.
Okay. So in other words, you took your original expression and kind of broke it up into smaller, simpler pieces. Sounds good. So what did you get when you integrated that expression?
I got 1/2 x.
1/2 x.
Oh wait. Oh, 1/2 t.
Now, this is a t problem. No x's allowed.
Oh wait, I even did that on mine. I have an x and then 2 t terms.
How embarrassing.
Yeah, so 1/2 t plus 3/4 t squared over 2. And that's all over 2. And then minus 1 over 4t. Yeah. Plus c.
Don't forget the constant. Yeah, which if we then wanted to simplify, I think we could simplify to 1/2 t plus 3/8 t squared minus 1 over 4t plus a constant. Thank you, James, for helping me to illustrate a point here. What's up with this dt term? Or equivalently, what's up with this dx term? Well, those are going to kind of mean a few different things to us later on. But the reason for now we include them at the end of the integral is they help us remember what variable is our problem written in terms of, and with respect to what variable are we differentiating. So when we see this sort of dt term show up at the end of our integral, what that's telling us is, hey, you're treating t as your variable and differentiating with respect to t. Because if you remember, back when we were doing stuff with like implicit differentiation, like let's say we were trying to differentiate the unit circle, when we wanted to differentiate both sides, we have to say, what are we differentiating? We're differentiating both sides with respect to the variable x. And so we write out the fact that we're differentiating with respect to x as sort of this d over dx term on both sides. Same basic idea is applying here when we write dt at the end of our integral. What that's telling us is you're integrating with respect to t, meaning all of your variables that end up showing up should be t variables rather than, in this case, x variables. Despite the temptation to take something like 1/2 and saying the integral is, 1/2 x. Depends on what's the kind of, with respect to what variable are you integrating. If this is a dx at the end of the integral, then this would be 1/2 times x. But the fact that it's a dt here means we need to treat it as 1/2 t instead. By the way, follow-up question. Could we have taken integral of 2t squared plus 3t plus 1 divided by integral of 4t squared? Just taking the integral of the top divided by integral of the bottom? Franklin?
You gotta simplify first.
Yeah. Just like how derivatives behave nicely with respect to sums and differences, addition and subtraction, but doesn't behave nicely with respect to multiplication and division. Same's going to be true for integration. You can't take a integral of a fraction and say it's the integral of the top over the integral of the bottom, any more than you could say that the derivative of something like 3x squared plus 5 over 2x squared minus 6 is the derivative of 3x squared plus 5 over derivative of 2x squared minus 6. No, no, angry face. You can't do that with integrals any more than you could with derivatives. With derivatives, we had rules like the product rule and quotient rule that told us how do you deal with derivatives involving products and quotients. With multiplication and division. But you can't just do derivative of first times derivative of second, or derivative of top divided by derivative of bottom. Same's going to be true for integration as well. Yes, Katie.
I'm still kind of confused on like I get the 3/4 t, but in like the first step, but why are you then like doing the 3/4 t squared divided by 2 and the 1/4 t to the negative 1 divided by negative 1?
I don't know, James, how did you get those things?
Wait.
So how did you get from here to here and from there to there?
Oh, the reverse power rule. So for the 3/4 t, you add 1 to the exponent, so that makes it t squared, and then you need to divide the t squared by 2. And then for the next one, it's 1/4 t squared, so or t to the negative 2, so you add 1, so it's t to the negative 1, and then that's divided by negative 1.
Yeah. So the whole idea is you're doing the process of reverse power rule to say whenever you're integrating, say, t to some power, you add 1 to the exponent and then divide by your new exponent.
Okay.
So t becomes t squared all over 2. T to the negative 2 becomes t to the negative 1 all over negative 1.
Okay.
Does that make a bit more sense?
Yeah.
Cool, cool. And then we had another step where we kind of simplified all of that.
Okay.
Combined the 3/4 and the 1/2 to get 3/8, etc. Right, Glenn?
Could you have pulled 1/4 out in front of the function?
Ooh.
Simplify some there.
Said something like, so for instance, if we had wanted to integrate, let's do this on sideboard because you probably can't see that. If we had wanted to integrate something like 3/4 t, I see. So you want it to say like, could we have done something like 1/4 times the integral of 2t squared plus 3t cubed plus 1 all over t squared? Just integrated all of that without the 1/4 and then multiplied your final answer by 1/4? What do you all think? That gets the Dr. Gerstel seal of approval. Just like how you, mainly owing to the fact, like just as we had a property with derivatives, constant multiple rule, that said you could pull constant multiples inside and outside derivatives, same's going to be true for integrals as well. You can take any constant multiple and pull it inside or outside of your integral. Now, here's something you could not do. You can't pull the t squared out. That would be wrong to do. But the 1/4, which is just a constant multiple applied to your whole thing, that is certainly something you could pull out in front. Good question. Alrighty, about x squared over 3 plus 3 over x squared. Aiden, what was your strategy for this one?
So I simplified it, not simplified, but I moved it, or I don't know how you say derived it, so 1/9 x to the third plus 3 over 1/3 x to the third.
Plus 3 over what now?
1/3 x to the third.
Like that?
No, put x to the, well, my final answer is 1/9 x to the third plus 9 x to the -3 power plus c.
Like that?
Yeah.
How did you get from there to there?
I added 1 to the top on x, or did the reverse power rule, and then I had to multiply it by 1/3, so then I get 1/9 x to the third.
I see.
And then for the second one, I just kept the x on the bottom, and I did a reverse power rule on the bottom and just moved it to the top when I finished.
Ah. So you did like reverse power rule on the x squared down there to get an x cubed?
Yeah.
I see. I would be careful about doing that.
Okay.
Mainly because I think that would actually try to be doing something similar to taking integral of top divided by integral of bottom, which you generally don't want to do.
Okay.
So I like the 1/3. I really like what you did with the 1/3 x squared term. If you do that, you'll get 1/3 times x cubed over 3, which gets not 1/9 x cubed. But for your 3 over x squared, what I would recommend is we do something similar to what we did over here with the 2 over x cubed, and rewrite that as a negative exponent first. Because if you do that, you'll get 3x to the -1 over -1 when you use the reverse power rule on x to the -2 power, which is the same as saying minus 3 over x, I believe. So in the end, this is what I came up with. So whenever you have this sort of fraction going on inside of your integral, it's best to try and either simplify your fraction first or rewrite to use a negative exponent before you try and do your integration. Because in general, it's never okay to just take, integral of the bottom of a fraction like that. So with that in mind, let's look at our last two. What's the integral of 0? With respect to x. So in other words, what do all of the functions look like that are going to have a derivative of 0?
Any constant term.
Yeah, just it has to be a constant function. So technically, you could just say that the integral of 0 is a constant c, meaning that any constant function is going to have a derivative of 0. Look, it's be the pirate's favorite letter, not the R, but the C. And then finally, last one that we looked at was 1 over x. I'm going to handle this one. I haven't had a chance yet, frankly. Don't be greedy. What I did for this one is I rewrote 1 over x as x to the -1 power. And then when I did the reverse power rule on that, I got x to the 0 power divided by 0 plus c. Everyone on board with that? I'm just going to stare at everyone until someone disagrees. Excuse me, Emerson?
Well, if you check your work by deriving what you got at the end, it doesn't match up.
Sure it does. If I differentiate that, I get 0x to the -1 over 0 plus 0, and then hey, the zeros cancel out, so I get 1 over x, right?
0 over 0 is sadness. So,
It's sadness.
yeah, that doesn't work. So if
Oh my gosh, I divided by 0.
So if you work backwards, if we go back to our
derivative rules, the derivative of natural log of x is 1 over x.
Holy moly!
So if you differentiate 1 over x, you should get the natural log.
Yeah. So you know how this reverse power rule says that integral of any of x to any power should give you x to the n plus 1 over all over n plus 1 plus c? That's going to be a rule that always works. Unless n is equal to negative 1. Because if you try to integrate x to the negative 1 power using the reverse power rule, you would be dividing by 0. And you don't want to do that. So Emerson, you were saying that since the derivative of natural log of x is 1 over x, that the integral of 1 over x should be natural log of x plus c?
Yeah.
I like it. Almost. Technically, it's the natural log of the absolute value of x plus c. Dr. Garstel, why are you doing this to me? Emerson's thinking. Isn't the derivative of natural log of x 1 over x? It is. And yet, we're still going to say that the integral of 1 over x is natural log of absolute value of x plus c, not just natural log of x plus c. And for those of you thinking, what sorcery is this? This is a question that will be answered in Standard 12. So we're going to come back to that question for a second of why is it natural log of the absolute value of x instead of just natural log of x. But in the next standard. But any questions or comments before we reach the end of this standard? So standard 12 is going to be a pretty quick. Or sorry, yes, right.
Sorry, quick question. So if the function said like 1 over x plus 6 would be natural log of absolute value x plus 6, would you put the constant in the absolute value?
So if we had something like that,
Yeah.
it would. Yes. Now, one thing I am going to say is that technically we don't know how to do this one yet, and because we technically need a advanced integration technique called U substitution in order to do that. But we will talk about that several standards from now. But yes, that is how you would handle something like that. So standard 12 is actually going to be a pretty quick standard. Standard 12 is basically the same thing as standard 11, except this time we're going to be looking at trig functions, exponential functions, logarithms, your favorite standard 9 functions, and talking about how do we integrate all of those. So let's 2, 3, 4, 5. Thank you. Where is everybody, Dave? Somebody left over. So, integration with trig functions and exponential functions and logarithms, for the most part, works just like you would expect it to. The whole idea is that we're still going to be looking at finding functions whose derivatives give us back the original functions. So, my copy. Someone steal my copy. Hayden, did you steal my copy?
Not that I know of.
Good, here it is. I found it. You're off the hook. So, here's a little bit of review. So, we said in the last standard that the derivative of sine of x is going to be cosine. The derivative of cosine was negative sine of x. These were formulas that we were able to derive using the limit definition of the derivative. Then using like the quotient rule and chain rules, we were able to get our other trig derivatives, that the derivative of tangent is secant squared. The derivative of cotangent, or cosine over sine, is negative cosecant squared. Or again, secant is 1 over cosine, cosecant is 1 over sine. The derivative of secant is secant of x times tangent of x. And that the derivative of cosecant is negative cosecant x cotangent x. These were all formulas that we derived back in Standard 9. And also in Standard 9, we found that if you take the derivative of an exponential function like a to the x, we get a to the x times natural log of a. And similarly, if we differentiated log base a of x, we got 1 divided by x times natural log of a. And what I want to do in Standard 12 is to use these formulas to help us find some antiderivatives, or to compute some indefinite integrals of some of these trig functions. So let's take a look-see. I tell you what, y'all are looking restless. Taylor especially. Am I right? He doesn't know what I'm talking about. What I would like for you all to do is to take a minute or so. I want you to compute the 4 integrals on the second page of the packet. So I want you to integrate cosine, sine, e to the x, and 3 to the x. And what I want you to do is to keep in mind, when you're looking for indefinite integrals of all these functions, what I want you to do is to find all functions whose derivatives are cosine of x, or find all functions whose derivatives are sine of x, or e to the x, or 3 to the x. So go ahead and take a couple minutes, and try not to cheat by just looking at the third page. And see if you can sort of use these different derivative rules to find formulas for the integrals of these 4 functions. So. Back to work. Serious business in here. If the x was a constant, that would be right. So you're right that it involves 3 to the x somehow, but I don't think it's that, because that would be something you need to differentiate with the product rule. We get to something kind of ugly.
Did I do it right for the last one?
No, that would be the x times natural function and all of them. Swoosh, swoosh. Sounds good to me. So let's come back together and talk about these. I'm noticing some interesting observations as I walk around the room. So let's start with the integral of cosine of x. So if we wanted to find the indefinite integral of cosine of x, we're going to be looking for all functions that are going to have a derivative of cosine of x. John Henry, what can we say about all functions that have a derivative of cosine? What are they going to look like?
I said sine of x plus c.
Are they going to be sine of x plus c? How can we check that? What would we have to do if we wanted to sort of check this answer to see if it's correct? Anna?
Take the derivative of that.
Yeah. If this is the correct indefinite integral, then it should be the case that if we differentiated any of the functions in this family, we would end up back with cosine of x. Well, if we were to differentiate anything of the form sine of x plus c, wouldn't you know it, we are going to get cosine of x. So I like it. So the integral of cosine is going to be sine of x plus c. Medo magneto. So here we're just kind of using our derivative rules, but in reverse. Sort of like what we were doing with reverse power rule in the previous packet. How about the integral of sine of x? What functions are, in other words, are going to have a derivative of positive sine of x? Okay.
Negative cosine of x plus c.
Negative cosine of x plus c, he says. Well, if we were to check that, if we were to differentiate negative cosine of x plus c is going away. Derivative of cosine is negative sine, so the derivative of negative cosine should be negative sine of x. But wouldn't you know it, those negatives are going to cancel out, and we would get sine of x in the end. I like it. Franklin.
Why would it be negative sine of x, not just negative sine of x?
Well, good question. I would say because of this derivative property right here. The derivative of positive cosine is negative sine, so the derivative of the negative of cosine would be the negative of the negative sine of x, according to our derivative formula from Standard 9. So it's kind of interesting. Integrating sine and cosine is a lot like differentiating sine and cosine. But when you're differentiating sine and cosine, sine has the positive derivative and cosine has the negative derivative. When you're doing antiderivatives, cosine has the positive antiderivative, whereas sine has the negative antiderivative, or integral, however you want to think about it. owing to the fact that when you're doing integrals, you're doing derivatives, but in reverse. How about the integral of e to the x? This one's funny, because if you take the integral sign and squish it down to look like an s, it says sex. We're real mature in this class. So, what functions are going to have a derivative of e to the x? Todd?
E to the x plus c.
Yeah, e to the x we said is its own derivative. So if we would also expect, if e to the x is its own derivative, we would expect it's its own antiderivative too. But of course you also have to throw in the plus c when you're doing the indefinite integral as always. How about this one? Integral of 3 to the x. That looks like it's saying sex if you're a hacker and you write your e's backwards to look like 3's because you think it makes you look cool. Okay?
Would it be 1 over natural log 3 times 3 to the x
1 over natural log of 3 times 3 to the x?
plus c?
I'm going to say I know it's not just that because there's got to be a plus c term at the end. Well, let's see. If we were to differentiate what Gabe's given me, we would be differentiating 1 over natural log of 3 times 3 to the x plus c. Well, the plus c would go away, as it always does when we differentiate. 1 over natural log of 3 is just a constant multiple, so it would just, I think, come along for the ride. 3 to the x has a derivative of 3 to the x times natural log of 3. Oh, hey. Swoosh, swoosh. And Gabe, I think I like it. Yeah, nice job. So, that's a good way of thinking about it. So what Gabe did was he essentially did this rule right here, but in reverse. This rule says that when you differentiate an exponential function, you get back the same thing, but multiplied by natural log of your base. To me, it would make sense that if we then wanted to go backwards, integrate an exponential function, since differentiating gives you the same thing times natural log of your base, makes sense to undo that, you would want to divide by natural log of your base. To get 3 to the x times 1 over natural log of 3 plus a constant, plus your constant c, of course, in the end. Any questions or comments about any of those things? So, in general, I mean, that's mostly standard 12 in a nutshell. In order to do any of these integrals of these scary looking functions, you're basically just doing a derivative rule from standard 9, but in reverse. That's kind of the main idea behind this standard. And if you go to the third page, I kind of give you a list of like general properties, like the integral of sine is negative cosine. The integral of cosine is sine. The integral of secant squared is tangent, owing to the fact that the derivative of tangent is secant squared. Integral of cosecant squared is negative cotangent, because the derivative of negative cotangent is cosecant squared. None of this is really stuff that's new at all. These trig integral theorems, it's really just taking the same things that we did back in standard 9 and just kind of doing them backwards. Starting, when you integrate, you start with the end result with the derivative and you work your way back to what must the original function have been. Where as always you have this plus c because the constant term on your functions could have been anything and it wouldn't affect what the derivative is. One thing I will mention, I'll go ahead and write this one down as a generalization of what Gabe did earlier, is that for any a greater than 0, a not equal to 1, it's going to be the case that the integral of a to the x, or sax, if you will, is going to be a to the x divided by natural log of a plus a constant. And the reason for this is since if you were to differentiate a to the x divided by natural log of a plus a constant, you're always just going to get, well, a to the x over natural log of a times natural log of a, which is just a to the x. When you differentiate an exponential function, you multiply by log of the base, natural log of the base. When you integrate an exponential function, same thing, but you're dividing by natural log of your base instead. So, Ty, we've talked about how to integrate trig functions. We've talked about how to integrate exponential functions. What's left from Standard 9 to talk about how to integrate? Ah, my goodness gracious. What was the other type of function we talked about in Standard 9 other than trig and exponential functions? Get it? Reagan?
Logarithmic.
Ah, logarithms. Integral of natural log is not something we're going to be doing in this standard. Believe it or not, this is actually a really tricky integral to evaluate. I'll tell you what it is. It's x natural log of x minus x plus c, if you're curious. But in order to integrate natural log of x, believe it or not, you actually need to use the product rule backwards. Does it look like it? Like, so what does this have to do with the product rule? We're not going to talk about that quite yet. That's an advanced integration technique. What we are going to talk about, though, is this one. The fact that we said that the derivative of natural log of x is 1 over x back in Standard 9, but I'm now doing a heel turn on you and telling you that the integral is going to be natural log of absolute value of x instead. So the question is, why is this? Like, why do we have to have an absolute value pop up inside of our integral? Morgan. What are values, what's the domain of 1 over x? Meaning, in other words, what real numbers can we plug into x and 1 over x and get an output that makes sense?
Any number except 0.
Yeah. For 1 over x, we could say that's defined for all x not equal to 0. X can be positive, and you can plug it into 1 over x, get something that makes sense. X can be negative, you can plug it into 1 over x, get something that makes sense. You just can't plug in 0 because dividing by 0 is bad. If we put up a quick graph of what natural log looked like, Nora, for what values of x is natural log of x going to be defined?
All positive values.
Yeah. Natural log of x is only defined for x greater than 0. That's the kicker. 1 over x is defined for positive and negative numbers. Natural log, only defined for positive numbers. What about the natural log of the absolute value of x? Where is that going to be defined? Meaning, what values can I plug in for x in the natural log of the absolute value of x and get an output that makes sense? James, any ideas?
Anything but 0.
Well, if we plugged in a positive number for x, we'd just be getting natural log of x, which is totally fine. If we plugged in a negative number for x, well, the absolute value would make it positive, and natural log of anything positive is okay, so that would also be okay. We can't plug in 0 for x, because natural log of absolute value of 0 is just natural log of 0, which is undefined. But natural log of absolute value of x is defined for all x not equal to 0. And I'm going to leave you with a tantalizing thought. Maybe it's tantalizing, I don't know. The fact that we say the integral of 1 over x is natural log of absolute value of x rather than natural log of x is because these are the same, but this one is not. Have a good weekend, everybody. We come back on Monday, we'll finish off, we'll have a standard 11 quiz, finish off standard 12, and then we're going to start talking about some motion problems. Firing cannonballs and Wile E. Coyote. Those of you who have family coming to town for family or for parents weekend, hope you have a good time with them. I know I'll be meeting some of them tomorrow. Otherwise, have a good one.